Today I'm going to be reading this paper called Retentive Network, a successor to Transformer for large language models. This is a recent paper by Microsoft Research and Tsinghua University. They propose a new architecture called Retentive Network, or shortened RetNet, that has these three computation paradigms: parallel, recurrent, and chunkwise recurrent. And they say the parallel representation allows for training parallelism, like a transformer is able to train multiple tokens in a sequence at a time. And the recurrent representation enables low-cost O of 1 inference. So this means that each token takes a constant amount of time to generate, regardless of whatever context length they're using. This is on per token, not per sequence. If it was for a whole sequence, it would be O of n. So that's just a different way of saying it. And they say it improves decoding throughput, latency, and GPU memory. This is another bottleneck, is GPU memory. And they say it doesn't sacrifice performance. And they have a third mode called the chunkwise recurrent representation that facilitates efficient long sequence modeling with linear complexity, where each chunk is encoded parallelly while recurrently summarizing the chunks. And they say it achieves favorable scaling results, and the things parallel training, low-cost deployment, and efficient inference. And it makes it a strong successor to Transformer for large language models. And they have some code that you can use. Here's their main comparisons to a Transformer. It uses less memory, has more throughput, less latency, and less perplexity as you scale up the number of parameters. Here they introduce some trade-offs in different architectures. Mostly that the transformer has O of n complexity per step, which is O of n squared for a whole sequence, and takes up O of n squared memory to compute the attention matrix. And they describe how RNNs have O of 1 inference per token and O of n memory. And that lets them kind of combine these ideas of a transformer and a recurrent network into this RetNet. And this lets them kind of get away with getting all three of these features. And here they actually go into the way the network works. It's very similar to a transformer with these residual connections and pre-normalization. Instead of the multi-head attention block in a transformer, they use a multi-scale retention block. And they use the same feed-forward module as a transformer. They describe RetNet encodes the sequence in an autoregressive way. You have some set of vectors based on the tokens, and you form a matrix out of that and go through each layer. This is pretty standard. Here they actually explain how the retention mechanism works. So they start out with a recurrent formula, and then they eventually make it parallel in a different representation. And they also start by treating the input and output as scalars, and then they turn them into vectors later on. Just to make the math a little simpler for now. So you can see this hidden state Sn is based on the previous hidden state plus some of the input, and every time it goes through this A matrix, which means that if you're multiplying repeatedly by this, you get these different powers of this A matrix. Right here, you see this power. This is a different way of representing Sn, and you multiply by this Qn matrix to get your output. And it turns out the Q matrix is actually going to be based on X, which is the input sequence. They say it's content aware. X is the content, and now Q depends on X, and so does K. Now, since you have this A matrix raised to a power, it becomes a lot easier to raise it to a power once you diagonalize the matrix. Here they use these complex values to represent all possible matrices, because sometimes you can't factor without using them. And here they represent each value as part of a vector, but it's kind of like a diagonal matrix where for each of these. So we can see, since you raise it to a power, these lambda and lambda inverse terms will cancel out, leaving one at the start and one at the end. And that also lets you absorb lambda into WQ and WK. So that means you will multiply. You're going to be multiplying by WQ anyways to get this Q matrix. So, and if you're going to be multiplying by lambda anyways, you might as well like pre-compute what Q times lambda is and just call that the new value of WQ. So you can kind of just merge WQ and lambda into WQ. So you could kind of ignore lambda, since it'll be like having two matrices in a row. You kind of just turn them into one, multiply them ahead of time. Same thing with WK. This lets you just write it out with this diagonal matrix. And then you can separate this this negative power and this positive power of this diagonal matrix. And then they say that we further simplify gamma as a scalar. So this is just a choice they make to have it just be a scalar, and it simplifies it a little further. Here, they turn this negative power into a complex conjugate, and they combine that with the transpose to get the conjugate transpose. And there's this formula here for that they'll use later. And the next step that they take is to vectorize the entire thing, treating v of n and o of n as vectors. And this brings them to a parallel representation. So they started with a recurrent representation, and now they have a parallel representation. And this one's going to be vectorized as well. The first thing I would point out is this matrix D, which is it's like a triangle, I think a lower triangle, where everything above is just zero. And this is very similar to a causal mask. They say it combines causal masking and exponential decay. The exponential decay comes from the fact that this gamma is usually going to be between 0 and 1 in the way that they set it up. So the tokens that are closer to each other will have more of an impact instead of just either 0 or 1. It could be somewhere in between. So they treat it as a mask right here with the Hadamard product. And the rest is based on the previous formulas. They have this big theta matrix. Each row is this little theta term. And they say it helps them train efficiently by, computing loss on each token in an entire sequence. Here they have some nice visualizations about how it works. You can see this parallel representation. Looks kind of similar to attention, where or self-attention, I guess, where these Q, K, and V matrices are based on X. Here they go back to their a more simplified recurrent representation. So you can see the current states are determined by the previous states, which is a recurrence. And they've a very similar thing as before. They have a linear projection of the states. But they also have this third mode that they used to accelerate training. They were able to separate the sequence into these chunks, and each chunk would compute retention within itself, and then they would take the last the end of the chunk and use that as like a summary, I think they say, and they perform retention with that. And they have to scale up this gamma due to the fact that these sequences are now longer per token. I guess the chunks are longer per token. Yeah, and then they split up into two terms: inner chunk and cross chunk. And the inner chunk is the same as before. Here they introduce two new ideas. They have this multi-scale retention, and they also have the gate, or the gated part. So the multi-scale retention splits up the model dimension into these sections of a length d, and there's h of these sections, and each of them goes through a different head with a different parameter matrix. But the multi-scale part refers to how each head also has a different value of gamma. They say, for simplicity, we set gamma identical among different layers to keep them fixed. So each layer has the same gamma assigned to each head, but each head within a layer has a different gamma. And you can see that gamma is computed to be very, very close to 1. And if it was 1, it would just be a causal mask, but they introduced different amounts of decay, of exponential decay, by changing gamma. And the second part they introduce is this this term here, this the gated part. It's another projection of X, but it goes through an activation function and is used as a mask. They say it introduces more nonlinearity. Here you can see some very, very short sections of code. You can see they can compute in parallel in only a few lines. And also recurrently is very similar. Chunkwise is a little longer, but not that long at all compared to most things. They also say they introduce some normalization to help training stability. There's a few things they also introduce later on. in the paper that they had to do. My guess is that it just happened to be a less stable architecture, especially with lots of layers. You could have gradients that explode. But apparently this normalization within each layer helped. Here they just talk about their pre-norm architecture. This is standard, except they replace the multi-head attention with multi-scale retention. And something interesting they note here is that they actually use the chunk-wise recurrent in training for longer sequences. So it wasn't just like a theoretical thing they added. Here's a little bit of a comparison between different architectures. You see the transformer has training parallelization and takes O of n time per token for n tokens, and O of n squared space, and has good performance. And they say that their model has equivalent performance while only using O of 1 per token in time and O of n in space. They also say the recurrent representation is employed during inference, which makes sense because it's O of 1 per token. Okay. They compare it to a few other methods. They say it's very similar to a certain type of state space model. And they say it's kind of different from linear attention. They say, let's see, with RWKV and AFT, they just compare it. I don't know if this is similar architecture or not, but it seems like it's kind of not a similar architecture. But they say theirs is better. Let's see here, the experiments. So they trained 3 different models at different parameter counts. And they say that once their model crosses about 2 billion parameters, it's better than transformers with the same amount of parameters. For the same amount of parameters, but it has better perplexity. Yeah. So they try to make some equivalent transformers with the similar parameter counts to make this a fair comparison. And here's another thing they talk about. They say they have a beginning of sequence token that helps with stability in training, but it also helps performance. I'm not entirely sure why that would be. Maybe it gives it a better starting hidden state. That'd be my guess, is that it learns a good starting state to start in. Here's some other comparisons where it appears that their network is beating a transformer. I'm not familiar with these tasks, but I guess it's good to see that. And they also compare how much memory it uses. Here it appears to use less, not that much less compared to a flash attention, it seems like. I wonder why that would be the case. Maybe it's that the model parameters take up most of the memory anyways. But they have an interesting note here that when they compared to flash attention, they didn't have their own equivalent of flash attention. And they say that that would further reduce cost if someone made that. It has the potential to further reduce cost. And they say that someone else might come along with that. Here you can see the way that memory usage scales with sequence length. You can see that it barely scales when the RetNet has longer sequences. It scales a lot more with the transformer. And also, they say that their throughput is constant up here, which is more throughput, and the throughput doesn't go down as the sequence length goes up. And they also say that their model has faster latency and that doesn't scale as much. These are all good things. Here they compare it specifically against models other than the transformer, but at a very small scale, only 200 million parameters. So I'm not sure how useful this table down here is, because it's at a very small scale and doesn't even compare against the transformer. But it appears to do really well here. On perplexity, seems quite a bit lower than some of these other models. Another thing they measure is they say if you remove the swish gating, remove the group normalization, remove the weight decay, the gamma decay, and only used one scale for gamma, all those changes would make it worse. So they say there that if you use all these tricks, it does better up here, and for every one you remove, it does worse. And they also say that if you have bigger heads but less heads, it performs better. And this is the same as above. They say that the swish gate and group norm improve the final performance, and that using multiple decay rates and decay rates other than 1 improves the performance. And they say if you reduce the head dimension and increase the number of heads, it does worse. So there's a lot of different studies they've done. So this is the conclusion. Very similar to what we've already seen. They say it's an ideal successor to transformers. I think that'll still have to be tested, especially considering all the tables that we've seen. It's not entirely clear that it does beat a transformer. And I'm going to show one more table at the bottom that is also a little strange. Here you can see that they have a table comparing RetNet to transformer. It has lower perplexity by a little bit, but they have this weird comparison where they only compare it by calculating the loss on the last 128 tokens out of a 2048 token sequence. So it does feel like they're like kind of cherry picking some numbers here, which is a little bit concerning. And it doesn't even perform that much better than a transformer in terms of this metric. So I think it'll take time to see whether or not this method is better than transformers or not. But it does appear to be very exciting. And promises a lot. So we'll have to see if it delivers on those promises. Thank you for watching this video, and feel free to subscribe if you want to see more videos like this. Bye.